Thanks for the introduction. Today I will present HCDN. This is a collaborative work between Peking University and ByteDance. Live video streaming platforms like TikTok, Twitch, and YouTube Live serve billions of users worldwide. To deliver live video at such a massive scale, these platforms rely on content delivery networks, or CDNs. In a typical CDN architecture, video streams are ingested by CDN origin nodes. Then they are streamed to geographically distributed CDN edge nodes, and then finally delivered to audiences. The nodes here are indeed CDN clusters. However, operating global live CDNs is extremely expensive. It costs platforms hundreds of millions of dollars annually for bandwidth. So in this presentation, we break down this cost to find optimization opportunities for CDN bandwidth cost. The total cost is driven by three key factors. First is the CDN edge price. This is the unit cost of delivering 1 byte from the edge to audiences. The second is the efficiency of the CDN tree topology. This is the CDN internal bandwidth induced per unit of CDN edge traffic. We measure efficiency here by the midgress-egress ratio, or MER. This represents the amount of CDN internal traffic induced per unit of edge traffic. The third one is the CDN internal price, which is the cost within the internal CDN topology to the edge. So we wanted to find opportunities to reduce these bandwidth costs. And to answer this, we did a measurement study on our prior production live streaming CDN. First, we look at the average price of CDN edge traffic. Traditional video on-demand CDNs use cheaper and best effort edge nodes like P2P nodes. So we looked at whether we can use similar opportunities for live streaming. Let's compare different types of available edge nodes on the market. Regular CDN edge nodes offer high quality of experience, or QoE, but they're expensive. PCDN nodes, which are P2P CDN nodes, are very cheap but suffer from low quality of experience. Actually, we use PCDN nodes for our video on-demand CDN. However, ISPs provide cost-effective edge nodes at a medium price point, but still maintains high QoE and capacity. And after careful analysis, we decided that these ISP edge nodes are a better fit for live streaming CDN. So we should integrate these nodes into the edge to lower the average edge price. And next, we examine the second factor, the efficiency of the CDN tree topology. We found that cold streams, which are streams with less audiences, are highly inefficient. They generate minimal edge traffic, but they still require internal traffic to fetch from the origin. The solution is simple. It's aggregating these cold streams onto only a fewer edge nodes. And this reduces redundant internal traffic and improves the CDN tree topology efficiency. And interestingly, globally hot streams can be locally cold on specific nodes. This happens due to uneven audience distribution, and this leads to similar inefficiencies as the standard cold streams. And this requires granular aggregation. We need to shift traffic specifically from cold nodes to nodes where the stream is already hot. Third, live streaming today involves various types of streams, such as full stream, substreams, and patch streams. A substream or patch stream might only request a small fraction of the video data. However, if there's a request for a substream or patch stream at the edge, the node often has to fetch the entire full stream from the origin via internal traffic in the CDN. So this amplifies the inefficiency of CDN internal traffic. So for this kind of streams, we must perform even more aggressive aggregation. Now we investigate the so-called frozen streams. These are streams that are extremely cold, with only very few audiences globally. They typically sparsely distribute across different regions and ISPs, and sometimes thousands of kilometers apart. So aggregating them is prevented by strict cross-ISP and cross-regional traffic restrictions. If we aggregate them, we would incur expensive overhead and penalties. And instead, we can offload these frozen streams to specialized multi-homed nodes. These are nodes with cross-region and cross-ISP capabilities provided. It allows them to fetch the stream directly from the origin without violating traffic restrictions. And for average price of the CDN internal traffic, our prior system already used a flat circular topology that minimized the internal price. So the presentation will focus on the edge price and the CDN topology efficiency. So to summarize our findings so far, we have 5 key optimization points. Offload hot streams to integrated ISP edge nodes, and aggregate cold streams to optimize tree efficiency. Shift hot streams from cold nodes to hot nodes specifically. Process substreams and patch streams more aggressively in terms of aggregation, and offload the frozen streams to integrated multi-homed nodes. Indeed, these findings drive our 2 design guidelines for the HCDN system. First, we must improve the CDN edge by integrating the 2 new kinds of nodes, the ISP edge nodes and the multi-homed nodes. And second, we should schedule the live streams among these nodes granularly. But implementing granular scheduling via typically HTTP redirection introduces extra round trips. This increases first frame delay and stalls, and might hurt users' quality of experience. The second challenge is about long-term strategy management. Over our 4 years of operation, continuously adding and modifying scheduling strategies led to a system that was hard to manage. And because we had to handle uncoordinated patches, strategy conflicts, and frequent cross-team collaboration. So we designed HCDN, a hybrid CDN system. We first enhanced the CDN edge. Layer 1 is the regular CDN edge nodes, and layer 0.5 for ISP edge nodes, which are cheaper. And layer 1.5, these are the multi-homed nodes for frozen streams. Central to HCDN is our scheduling framework called OpenTiga. It has a central orchestrator that computes redirection rules periodically. For strategy management, the orchestrator provides a unified abstraction. Every strategy must implement the standard primitives. The orchestrator runs periodically. It decouples policies from core mechanisms and resolves conflicts. It only uses fine-grained state collection for hot streams to reduce overhead. To solve the QoE challenge, the OpenTiga client implements proactive quality assurance, or PQA. This client interacts with the recommendation system. It predicts swipes and establishes connections and pre-pulls streams in the background so that the streams can play instantly. So with OpenTiga, we implement our 4 strategies. The first is frozen stream offloading. It redirects frozen streams from regular layer 1 nodes to the multi-home layer 1.5 nodes and minimizes internal traffic. The second is cold stream aggregation. For standard cold streams, we redirect traffic from scattered layer 1 edge nodes and aggregate them onto a smaller dedicated subset of layer 1 nodes. Next one is hot stream aggregation. For globally hot streams, we identify that the specific layer 1 nodes where the stream can be locally cold. We then redirect the traffic from these cold nodes to the nodes where the stream is already locally hot. And this finer grain approach trains the cold nodes and reduces the redundant internal CDN traffic. And the final one is hot stream offloading. It redirects hot streams from regular layer 1 nodes to cheaper ISP layer 0.5 nodes, and this is to lower the CDN edge price. We only offload hot streams here, so we can make sure we don't accidentally increase the internal traffic on these alternative nodes. HCDN has been deployed globally. Compared to our old system, it reduces the migress-egress ratio and lowered the average edge price and reduces overall bandwidth cost by over 30%. The incremental deployment of HCDN over the past 4 years shows the impact of the system. We added cold stream aggregation, the CA in the figure, and followed by the frozen stream offloading, and then hot stream aggregation. And the process successively drove down the migress-egress ratio and decreases the relative cost of the CDN bandwidth. And similarly, we progressively roll out hot stream offloading, and this process steadily decreased the average edge price and hence the overall relative CDN bandwidth cost. The system overhead remains very low. The controller memory is under 300 megabytes. The edge node memory is negligible, and the control bandwidth stays below 150 megabits per second globally. And finally, we measure the QE performance in an A/B test. Redirection without our proactive quality assurance noticeably increased the first frame delay and number of stalls. However, when we enabled redirection combined with the proactive quality assurance, the QE metrics were not only fully restored, but were actually comparable to or even slightly better than the baseline without redirection. The proactive pre-pooling effectively masked all network scheduling latencies. In conclusion, HCDN demonstrates that augmenting edge infrastructure and coordinated fine-grained stream scheduling achieves massive cost savings without sacrificing the user quality of experience. And thank you for your attention, and I'm now happy to take any questions.